Welcome to our Sentinel Hub webinar. My name is Sabina and I want to welcome you on behalf of our entire Sentinel Hub team. You probably already know us from other webinars. Otherwise, you will get to know us today. As you know, my colleague Munia Shebela will give you a detailed introduction to the Statistical API, which builds on our Process API and custom scripts. Both have been already presented in our previous webinars, and the recordings are available on our YouTube channel. Munia's presentation will be followed by questions and answer section, and she will start with the agenda shortly.
Today, we will dive deep into Sentinel Hub's relatively new statistical API, which is a very powerful tool that allows you to calculate different kinds of statistics for your data. So, in general, if we ask ourselves what kind of statistics can you gain from this, we are talking about average values, maximum, minimum, standard deviation, pixel count. You can create histograms. You can calculate the values of certain percentiles and so on. So first, we're going to take a look at how Statistical API actually does this, how it calculates statistics, and how this compares to if we were doing it all ourselves using just Python. In general, during this webinar, we are going to be working with Request Builder and Python. Then next, we are going to try to understand Statistical API results and see how we can configure multiple outputs, how you can manipulate naming. And then we will also look at aggregations. We will think about how mosaicking impacts this. We will check dataMask and also pixel exclusion. So it's a really cool feature of Statistical API that you can actually exclude certain pixels that you do not want included, such as, for example, water pixels from your NDVI calculation. Next, we will check how we can make custom calculations and histograms. We will spend some time diving deep into what kind of histograms you can make, what are the options available to you. And then we will also look at how you can use Python to retrieve any value from JSON. We will also create loops in Python to access statistical data and return a line chart. And lastly, we are just going to quickly mention Batch Statistical API. All right, so let's jump to our Jupyter Notebook first. So how does Sentinel Hub API calculate statistics? Well, essentially what Sentinel Hub does, it first gets an image and then it calculates statistics on top of that. So first, let's see how we would do this ourselves without the Statistical API at all. So after authenticating, we have here defined the area of interest and our eval script. Our eval script is returning the NDVI. So we are calculating the NDVI statistics. Then we have a bounding box. And now what we are going to do, we are going to run the process API and then calculate statistics on it manually using NumPy. So after running the process API request, which is nothing special, we just get an image. We can then also display this image so you can see this is our polygon. And we can also figure out how many pixels exactly it has. So we basically multiply the x and y axis here, and we figure out that our polygon has exactly 1,100 pixels. Then we can use Python to calculate minimum value, maximum value, mean, standard deviation, histograms with 5 pins, and several percentiles. To do this, we use specific NumPy methods, such as non-mean, which is going to, if you call it to your request results, going to return the minimum value, and so forth. This is the result that we get from manual calculation of our image. You can see we have all the statistical information. Then we have a histogram here, which has an array of how many pixels are in each bin, and then also some bin borders. You also have the values of the percentiles over here. And okay. So now Statistical API essentially does the same thing. It gets an image first and then calculates statistics on top of it. So we would now, if we now run the Statistical API, we are now not going to go deep into the structure at this point, because we will do this later using Request Builder. It will be much easier. However, just to note, we are calculating statistics for a single day, as we did above. We have the same bounding box, and we are again calculating the percentiles, and we want a histogram and so forth. And this is then the result. So an important thing is that statistical API does not return images such as process API, but returns JSON responses. And this is a JSON response. This is how a statistical API response actually looks like. We will look later deeper into how you can decipher all that and what everything means, but already you can see that we have minimum values here and we have a histogram over here. So if we compare them right now, on the top we have statistical API result, and on the bottom here we have our own manual calculation result. Now if you took the time, and you can do this later because this notebook is going to be published on our GitHub repository, if you take the time you will notice that the values are exactly the same. Okay, now let's jump to request builder and let's create our first statistical API request. Here I have drawn a custom polygon in an area near Rome. And we are going to first try to create statistics for just a single day, just as we did now manually. And we have selected the February 1st to February 2nd. We are using Sentinel-2. And here, this is a very important part of the statistical API, that you can specify actual aggregations. Just wait a second, because this will all become very clear. However, just note that the P1D means that we want one-day aggregations. So this is going to allow us to get just a one-day, because we have a time range set to only 1 day.
However, if we had our time range set, for example, from February 1st to the end of the month, then we would get several different outputs, as you can see later.
All right, here is the eval script, which is for now just returning the NDVI calculation. And here in the calculations and histograms, we just have default selected, which means that we will just get minimum value, maximum, standard deviation, pixel count, and number of no data pixels. Here on the right, you can see the request preview window, which you can update automatically as soon as you update the user interface of Request Builder. Let's run this request. And immediately we can see that something went wrong. We got an error. We did this intentionally because we wanted to show that in case there is no data available for your time range, you are going to get an error. And as you can see, our data array over here is empty. This is because in this specific day, there simply wasn't a Sentinel-2 image available. However, if we now jump to February 4th to February 5th, and another note, let's quickly scroll down to the time range. We see that the time is set from midnight to the first day to the end of the day of the second day. So we get the full range of hours in these 24 hours available. Now, if we send this request, we actually get statistics. And here we can see we only have one interval for this day. And we can see statistics here. We have minimum, maximum, mean, standard deviation, sample count, and no data count. You also see that we have our calculation here is named data, and the band over here is named B0. The B0 is just the default naming, and a bit later you are going to learn how to control that. Next, let's create a request for 6 months, aggregated by months, so that we are going to get 6 results. To do this, we are going to have to go to the previous year, 2021, July. Let's go to, not actually from January 1st to July 30th. Why July? Well, because this is how the days actually distribute. If you would put January to June, you would actually only get 5 results back. And now over here, before we had 1 day, you could also have 30 days, 50 days, whatever. Or you can say 1M. This is now going to be exactly a 1 month calculation. Another important note, I'm not going to dive deeper into this. However, you have several options here with which you can control what to do in case your time range isn't divisible by your interval. All right, so let's run this request and let's see what happens. Okay, so now we can see that we have 6 different intervals here. If we click on the first one, from January to February, we get the statistics. you can remember the minimum value of 0.2. And if we go to another one, the value changes. This is because this is a very powerful option with Statistical API, because it's kind of like several requests being packaged within one. So these intervals over here are kind of similar to time ranges of the process API request. And Statistical API gets, because by default the mosaicking is simple, don't get confused about this, we will talk about this a bit more later. It will only take one scene for each of your interval, and then it will calculate statistics on top of that, just as we did before in Python. So each of those intervals has statistics calculated on one of the scenes from that interval. So the next thing I want to show you is how easy it is to change the collection. So let's say that we want the latest Landsat 8 L2. To do this, we can just jump to our documentation, data, Landsat 8 L2, and we can check the data type identifier, which we see that it is Landsat 02 L2. So we can now easily select the correct one, Landsat 02 L2. But what we also can't forget is the eval script. We also have to modify the bands. To do this, it's just easier to jump to our custom scripts, go to Landsat 8, check the NDVI, and we can see that the NDVI for Landsat is composed of band 5 and 4. So let's just change band 8 to band 5 everywhere where we need to. And we are now ready for Landsat. You can also see that the collection has updated itself in the request body itself. So if we run this request, it takes a couple of seconds because we are calculating it for 6 months. And now we got the statistical calculation available for Landsat. The next thing we're gonna check is how you can manipulate names and outputs. So let's first leave it as it is, and let's just try to change some naming. So here in the output, the first thing that is important with the Statistical API is that dataMask output is mandatory. We will explain this later when we will show a couple of examples of what you can do with dataMask and what it actually does. But for now, it is mandatory, so it is why it needs to be here. So with eval scripts, you have to specify each output here in the function setup, and then also reference it in the evaluate pixel function. If you're not familiar with custom scripts, check out our custom scripts webinar, which is also published on our YouTube channel. So let's say that we want to rename this, our output, and also that we do not want to get the result B0, but called NDVI. Okay, so this can be called anything. For example, we can call it data. And of course, we then also need to reference this down here to be called the same. And now this is the array of outputs that we have for our first actual returns for our actual output. And it is only one here. We could have several, we could have up to 3. And to actually name it. And also we are going to lower the time range so that we won't wait so long. Okay, so now we see that our output is named my data and that the band is actually named NDVI because this is how we called it. Okay, so now let's continue with this a bit. And also what I want to do, I want to go back to Sentinel-2 right now. So I will just replace these 2 bands again to band 8, as we will be working with Sentinel-2 from now on. Okay, so
we can return several bands within each output. Let's add bands 8 and 4 to our My Data output, and let's call them red and near infrared above. The first one is near, and the second one is red.
You can name them anything you want, but be careful that the sequence of the name elements here match the sequence of what you're returning here. I made a mistake over here. Here it should be band 4, like that. If you're going to switch this naming, then the results are going to be very confusing for you. So if I run this request now, you can see that the My Data output now contains NDVI, near infrared, and red outputs, and statistics calculated for each one. All right, so another thing you can do, you can output as many different outputs as you like. So let's, for example, call the other one SWIR, shortwave infrared. And in it, let's return the bands 12 and 11. I am naming them already, even though I didn't yet add them into the evaluate pixel function. Also, don't forget that anything you call in the evaluate pixel function, you actually also need to add in the function setup. So let's add in band 11 and band 12. And now we also need to reference this output down here with the same name, of course. And the name is, in our case, shortwave infrared, or just like that. And now we have to actually call in the correct band, which we do like this. So let's check if the naming matches the sequence. It matches. Do we have all the commas? Does the name match? Okay, it all looks good. Let's try to run this. And now we see that we have two outputs. We have the shortwave infrared output with our two bands. And then if we check the my data output, we have all these three bands. So this is how you can control the amount of outputs and the names. So the another thing that is important, if you click to download the response, you are going to get the full JSON file downloaded, which is going to include statistics for every interval. So not just one and one, but all of them. So let's quickly have a peek at that document. So as you can see, all of the information is contained within the data structure. And if we jump a bit down, you can see that we have several intervals. But to understand this a bit better, let's jump to our presentation. So just very quickly here, I would just like to show you how the example of the eval script corresponds to the output JSON response. And here I have noted the interval 1 and interval 2 in yellow. So you can see that data for the first interval is contained right here, and data for the second one right here. And then in the outputs, we have our output data and our band, which is in this case named B0. So what would happen if we did not name the bands NDVI and band 4 here, but still listed several outputs? Well, we would get B0, B1, B2 named by default. So this is why it makes sense to always name your outputs. And then our actual NDVI calculation from the case 1 is here in bands. Then in the second case, we just see the example for the 2 bands. So we can see that our output now contains 2. And then the third case just shows you what we already saw, how 2 different outputs actually impact the resulting structure, where you get the 2 separate outputs that each of them then have bands inside that correspond to the actual returned output. All right, let's quickly jump back to our agenda to see what we have covered. So now we have checked how we can understand results and control multiple outputs. And we also made a couple of simple requests. So before we continue to aggregations, datamasks, and so forth, we are going to jump to Python. And we will quickly see how you can run any statistical API request in Python. I will first update my credentials so that my token is updated. All right, so in order to do this, you can run any request just by simply changing this curl to shpy and then copying everything and pasting it in. Then you just need to do 2 things. You need to replace your credentials here. I have them set as variable above, so I can simply call them as client ID and client secret. And then down below, you can also actually output this response. And here you see that we have run the request successfully. Here we have also in Python simply how to run the request for a single day, which we already did. You can check this later in the notebook, how the Python corresponds and how the structure looks like. However, now let's check how you can easily run any request from documentation as well. So we have our statistical API documentation on our doc sentinelhub.com. You can find all the information here, all the options, and also examples. There are several cool examples here. Feel free to check them out. However, just to run the request, all you need to do is just pasted in the request from documentation. And as long as you are authenticated, you are going to get a result. So this is a statistics for band 4. And we see it over here like this. Okay, now let's quickly jump back to our PowerPoint presentation. And let's talk about, just very quickly, about mosaicing. As mentioned before, in case your mosaicing is set to simple, which is default, if you have mosaicing simple, you're going to get precisely one scene within each of your intervals. So which one exactly is going to be selected is based on your settings. By default, it is set to most recent one is going to be taken, but if you set it to be least cloud coverage, then the one with least cloud coverage is going to be taken. So that scene is then fed to the calculation, and the calculation is done on top of that image result. So mosaicing can then, for your area of interest, for example, stitch together several different scenes and then calculate statistics on top of that. This means that here the aggregations are only done spatially. This means that statistical API takes all the pixels within your area of interest and figures out what is the, between all of them, what are the maximum values, minimum values, and so forth. So it only takes into account different pixels within the area of interest, so only spatial aggregation. If you would like to do temporal aggregation, you would need to use multi-temporal scripts. So what does this mean? Let's say that you want to, instead of just to have one scene taken for each interval, let's say that you want to get the average NDVI value that is averaged across all the scenes that are available to an interval. Well, in this case, you would use in the multi-temporal script either tile mosaicing or orbit mosaicing. In tile mosaicing, you are going to get as many scenes as there are tiles available within your aggregation interval. And with orbit mosaicing, you're going to get as many orbits as they are available within your aggregation interval. However, note that you need to tell the eval script exactly what you need to be outputted, because the output is going to expect one scene. So, for example, you need to tell the eval script in the evaluate pixel function, okay, I actually wanted minimum NDVI value out of all the scenes in my interval, each of the intervals, or you want the maximum value or anything like that. So we will not go into details about the multi-temporal scripts because we have a webinar on that. So feel free to check that out. And that webinar also goes deep into explaining mosaicing, which is also very relevant for this use case. We're going to just quickly check the statistics of maximum monthly NDVI in our documentation, where you can see that in the eval script, mosaicing orbit was called in, and then the maximum NDVI was returned. So let's jump back to our agenda. Okay, so next, let's check data masks and the pixel exclusion. Back to the request builder. And I will just default back to my initial request, which I have saved here. This is also a very easy way how you can share statistical API requests with others. You just copy them, the curl or Python request, and then click parse. And then everything will be automatically updated. So we are now back to just returning the simple NDVI. All right, so why is dataMask output mandatory in statistical API? So dataMask is a parameter in Sentinel Hub that figures out which pixels in your area of interest carry no data. Let's suppose that we have a polygon that is shaped like this. So you might expect that statistical API is going to take only the pixels within this polygon, but this is not the case. It is going to take the whole rectangular bounding box that encompasses it. And that bounding box has a lot of empty pixels here and here. So it is absolutely necessary for statistical API that no data pixels are excluded, because it would just not work for the statistical calculation. Let's check this for a second. First, we are going to return 1 here. Why 1? Well, because you can read in our documentation in the eval script and the transparency guides, it will all be linked in the description. You can see that if data mask is 1, that means that there is data. And if it is 0, it means that there is no data. So we have now, with this 1, essentially forced the system to interpret all the pixels as that they carry actual data. So if we run this request, you're going to see that 0 pixels went into no data count. This means that no pixels were excluded from the calculation. If, on the other hand, we actually run the dataMask, if we actually return dataMask out here, this is going to return dataMask 0 for every pixel which doesn't have data. And if we run this now, you are going to see several pixels where quite a lot of pixels were excluded from the calculation. So this is why this is so important. You can also exclude pixels in general from the eval scripts, and this is really cool. For example, let's say that you're interested in the NDVI of an area where close to water, let's say around the Fiumicino, and you want the NDVI of the area, but you don't want your NDVI to be skewed by water. I mean, you might want to be searching for chlorophyll content of the water, but maybe you're just interested in like the dense vegetation forests and so forth, and then you want water pixels excluded. But this is easiest to do with Sentinel-2 because Sentinel-2 has several very cool bands that are very useful. So let's quickly jump to Sentinel-2 L2A documentation and down to units. And here you can see that we have the SLC scene classification mask. And this scene classification mask has certain values that corresponds to certain land covers. For example, we can see that water corresponds to number 6. You have several other interesting like snow probability and so forth that you can use. So in our script, what we would do, we would now set the variable called whatever you want, for example, water mask. And we would say that it is a 1. And then we would just create a simple if statement. When we call in the SLC band, we go samples.slc. And if that equals to 6, which we know is water, then we want this water mask to be 0, equals to 0. Don't forget to add the band if you are using it. Otherwise, you are going to get an error. Let me just check quickly if it's SCL. Okay, SCL. So SCL. Okay, and also don't forget the comma. And now what you can do, so this doesn't yet do anything. If you now multiply this water mask, we had one parenthesis too many. If we now multiply this water mask here with the data mask, you are essentially telling the system to exclude both no data pixels from data mask and water pixels from the water mask. This is because if we multiply it, then whichever of them is 0, it is going to result in 0 for that pixel. So hopefully I did everything correctly now, and we do not get an error. We can see that several pixels have been excluded from the calculation. Good. So yeah, let's quickly jump back to Python. So because I want to show you another interesting example. And this is an example of that calculates NDVI and barren soil index statistics with water pixels excluded, but not only that. What this script does is it first calculates the NDVI and barren soil index, and then it returns it each in its own output, as you can see right here. But the most importantly, what I want to show you is that this pixel does not only exclude no data and the water, but also excludes those pixels that are not valid based on the values of the NDVI and barren soil index, for example. And the way it does that is it creates another variable called valid NDVI mask, calls it 1 again, and then it just checks if all the bands are equal to 0. If they're equal to 0, that means that we want to exclude these pixels, because when our no data pixels are also 0, this could skew our calculation. So yeah, another important thing that you can do, and it's important for statistics, if we quickly jump back to our presentation. So you can see that especially if you are working with tile mosaicing, so you can have clouds between your scenes. It is very easy to get rid of clouds by just simply turning on the advanced options and lowering cloud coverage. which is actually going to get rid of tiles which have cloud coverage larger than this, so they will not even come into an account. Let's jump back to our agenda. All right, let's check histograms and custom calculations now. So going back to, I'm just thinking what would be the best time range. I think we should go for the summer months for the histograms, so that we're going to get some nice vegetation. So let's change our time range to, let's say, here, and also to, let's aggregate it to 1 month, or we can also do 2 months. Let's leave the cloud coverage alone right now, and also let's navigate somewhere where we know there is a lot of vegetation, such as, for example, here. So we are going to see as big of a NDVI range as possible. So now I'm just going to Control Z a bit to get back to my original NDVI calculation. Okay, so this is it, returning simple NDVI, all good. So we can now add statistics to this, and we can specify exactly which band we want to add statistics to this. So this would be important if we had next to NDVI here also band 4, and then we could calculate the 50th percentile for band 4 and the 90th percentile for NDVI, for example. So if we say 90 right here and run the statistics, it is simply going to add the percentile statistics on top of the default statistics that we have already. You can handle different outputs if you want to specify which output should get which statistics by adding a calculation, and then you get everything repeated, the histogram statistics. So this way you could have, for example, 3 different outputs, all with different bands, and each one could have its own histogram. And you can also see an example like that in our documentation at the bottom, where you can see multiple outputs with different data masks, different histogram types, and so forth. All right, so we're going to delete this second calculation now, and we are going to look into histograms. I will click Add Histogram. And as you can see, again, I can apply it to any band, but I will just leave it by default to be applied to all bands. And we have 3 options of histograms right now. We can create a histogram by number of bins, by bin width, and bins array. Now let's jump to our presentation to see what this all means. So first of all, this is a histogram as Sentinel Hub returns it. And let's first talk about a couple of terms. On the y-axis, we have count, and this is how many pixels there are in each bin. It is just a number of pixels. And then on the x-axis, we have bins, which is the output value. So if we are calculating NDVI, then this is the NDVI value. It could also be reflectance value, brightness, temperature value, or even a discrete value, whatever you are working with. And then these towers over here are called bins. In our case, we have 5 bins. And then a very important part of the histogram is that its lower edge and higher edge are quite important. The lower edge of the whole histogram is called low edge. So if the user does not specify this, just the minimum value available in that interval is taken. And here is just the maximum value. So in our case, this is 0.85. And if it is not specified, again, the maximum value will be taken here. The edges of the bins also have low edges and high edges. So the low edge of this interval will be, for example, a bit lower than 0.0, and the high edge would be just below 0.2. So we have 3 general options. The first 2 make equidistant bins. And the first one, we specify the number of bins. So for example, if we say 5 bins and nothing else, then the full range of the NDVI, if we were, let's say that we're just working with NDVI with all the examples, the minimum and maximum values in the interval are taken, and we have 5 bins. If we say 50, of course, we will get 50 bins. So it is just distributed so that 50 bins fit into the full range. The bin width, on the other hand, specifies how wide a specific bin can be, and then each bins are equally wide. So this one has 0.05, this one has 0.1, and as you can see, this affects the number of bins so that they can fit into the range of the NDVI. Then the third option is that you can specify exactly where your beans are going to start and end. This allows for unequal bean widths as well. So here, as you can see, you can specify 0.0, 0.4, 0.8. This is the input that we're going to put in. And then you get exactly 2 bins, from 0.0 to 0.4 is the first one, and then the second one to 0.8. On the example below, you can see the example of how we got an unequal bins. So we have the first bin from 0.4 to 0.5, and then the next one goes from 0.5 to 0.8. It's quite big. And then the last two just go to 0.85 and then to 9. Okay, so now let's try to create such examples. Let's specify the number of beans 5. And let's see what happens. It's just calculating. And there we go. We see 5 beans now. And we have 2 intervals. Each of them gives us a different histogram because, of course, each one is calculated on a separate sample and thus has different statistics. You can always download histograms as images if you want. All right, so now let's try 50 beans. I forgot to mention here in the request preview, you can easily see how this is structured. So this is actually the request that is being sent. The user interface is just building this request. So here we are specifying the number of beans as 50. We will now get 50 beans, and there we go. It's also here you can also check that most of the values fall between 0.2 and 0.8 with the NDVI. Another very important thing that I forgot to mention is that with process API request, the default format of your data is auto, which means that that values are scaled to 0 to 255. However, with statistical API, the default is float 32. This is because most often people are calculating statistics on NDVI and indices, which have decimal values, often ranging from -1 to 1. So this is why this is default. However, you can always change this. If you are, for example, working with scene classification, it is better to use unsigned integer 8 because you just need integer values. That's why our histogram is between 0.2 and 0.8, is because we are using floating values to allow for these decimals. Okay, so now let's try some bin width. So in our presentation, we had 0.05, for example. You always have to specify. You have to specify the actual parameter here. You can't just enable the type of it and then just you're gonna get an error. And here we can see that as many beans were created as there were, so that it fits our bin width. So each of them we can see is about 0.05 wide. If we had 0.01, again, we would get a lot of bins within this value. So let's wait for a second with the low edges and high edges, and let's check what the bin array does. So we said that in bin array, you can specify exactly the values of your array. So for example, I could say 0.2, and then I could say 0.3, and then 0.9 directly. And now let's see what's going to happen. And you can see that we got 2 bins, one of them smaller, from 0.2 to 0.3, and then from 0.3 to 0.9. I have a cool example how you can actually use this. And we are going to use scene classification to figure out how many pixels are in specific land classifications, and we are also going to put some of them together. So this is an image with process API request with the scene classification that we got. I will just quickly show you where I got that in our custom scripts. So if you search for classification, scene classification, here is the eval script that we used. And here you can see the legend. So you can see that the blue is water, the green is vegetation, yellow is non-vegetated, and so forth. All right, so back to the presentation. So here are the values of this scene classification, which we have also seen before in the documentation. So the idea here was that, for example, we do not want any no data, saturated, dark area pixels or cloud shadows, but we want to start our histograms with histogram with vegetation, and then we want bare soils, water, and then we want to merge all the clouds together, and then also display snow and ice. So what we did, we specified our beans array as starting with 4, then going to 5, 6, 7, 11, and 12. So what we're actually doing, what we're doing here is, if you look at the histogram down below, you can see that the beans are exactly as we have specified them, 4 to 5, 5 to 6, 7, and then from 7 to 11, and then 11 to 12. Because these are integer values, the actual, what is happening, what this represents falls to the left side of the bin. So the 4 over here displays vegetation. The 5 here, this bin 5 displays bare soils. And so we had a problem at the end, because if we just ended at 11, then our cirrus and snow and ice would be merged together. So we just added another one, 12, which goes essentially out of the range of the scene classification, so that then the snow actually falls on the 11 over here. And these are the bins that we have. So we can just, 4, 5, 6, 7, 11, 12. I have the calculation saved already over here. I will parse it so that we are quicker. And as you can see, this is the area of interest that is selected. This is the time range. We are looking at 1 month. In the eval script, we are returning the scene classification in our output. It is over here, so we're not returning NDVI, but scene classification. And then we have a histogram turned on, and here we have the bin specified as we just said. And then if we run this request, this is what we got. So we got in this specific time range, the distribution was like that. Here it was like this, and this is now really cool because we can now exactly check how many pixels were cloudy, because we have merged all the clouds together, and this was 13,734 pixels in this specific interval. Okay, so let's now return back. The number of bins and the bin width also have these low edge and high edge values. And now let's jump back to the presentation to see what they do. So what this does, it allows you to specify the edges of the whole histogram, so the low edge and high edge. If we just specify the number of bins or the bin width, then you are going to get the minimum and maximum values as edges from that interval. But here you can just specify what you want. To illustrate this better, I have created here just a request with 5 bins without any low edge and high edge specified, and you see it went from -0.2 to 0.8. And now let's say that we see this histogram and say, okay, but we want only the histogram that goes from 0.3 to 0.8, and we want it to have 5 bins within. Well, this is how you can use this. So if you then specify low edge and high edge as such, you're going to get 5 bins within this range. All right, so basically you just take a part of the histogram and just change the upper and lower border. Here's another example of the 50 bins, where we have decided that we only want values from 0.0 to 0.2, and this is how we specified the low and high edge values. And then 50 bins, as you can see here on the left, we only have several bins within this range, but here then 50 bins are put into this new range that we have specified. Now let's try to run this. We are going to say, for example, 50 bins, or let's say 30 bins. And then, for example, 0.2 to 0.5. And let's see what happens. Now we are at our SCL eval script. I will just quickly parse my original one so that we are quicker. And there we go. We are back to NDVI, back to our the polygon, but yeah, I just want to see some more vegetation. And we are now adding the 30 bins, and again 0.2 and 0.5. Now let's run this. And as you can see, this is actually a really cool histogram that appeared right here. And we have 30 bins right now, exactly between 0.2 and 0.5. You can see that Statistical API allows you to quite control what kind of histograms you are getting. Okay, let's jump back to our agenda. Okay, so now we are at Python visualization. So jumping to our visualization notebook, I will now quickly just show you how you can retrieve values from JSON and visualize charts. So for this, you need some basic understanding of Python, but we will just quickly say what we did here. So first, we have run a request, which we have seen before, which calculates NDVI and barren soil index with excluded water pixels. And then this is the result. We have specified a longer time range of a full year. And now, in order to find any value, you first have to reference the actual output, the name of the output, and then you need to understand the path to that value. This is maybe easiest done in our presentation because it has a nicer structure. So if we see right here, because we have very nice indentations, it is easier to look at it here than in Python. We can see that we would have to get to the mean NDVI value here. We would have to go data and then outputs. We jump over interval because we are not searching for them right now, and then data, bands, NDVI, mean. It is just the path from top to bottom. And in Python, I will now scroll up a bit to see the top of the response that we have gotten. We can see the same thing here, just that it is indented so that it is a bit harder to understand, but it is just the same. We go data, outputs, BSI, bands, BSI, stats, minimum, for example. And scrolling down a bit, if we do that, you then get exact value. In this case, the barren soil mean statistical value, but because we have several intervals, you can here specify which one you want. So this is the third one. We can also specify the first one or any one. You can end this search anywhere. You can end it at outputs, and then you will just get the content of everything that is in outputs of the second interval. So in order to create a line chart, what we want to do, we want to create a line chart that is going to show us some temporal distribution of NDVI values in our area of interest. And to do this, we have to access every instance of the specific value within our response. And for that, we have to create a loop. So we just create a loop that checks for every item in our response. And then we have to create another loop because that response has several items inside. It's an array. And then we can just access stats and mean. And of course, here you have to just mind the path. And now what we have gotten is the list of all the mean NDVI values within our response. So in order to create a chart, what we need to do now is we need to retrieve not on the mean values, but we also will retrieve the maximum and minimum values, and then we will plot all of them on the same chart. And we also need to find the date, because on the x-axis, of course, we want to have some date displayed. And to do this, we again create a loop, but in this case, we go into interval and 2, for example. So just it's a different path. Then what we do is we create empty arrays and we append all of this data into these empty arrays and then just print them out. This is how this looks like. These are the arrays. The first one has dates and then our values. Another thing, we have also limited our date string so that it doesn't include the milliseconds and all that, but just a nice date. Then an object was created so that it is easy then to create a table. So the first parameter here is the name that we want to see in the table, and the second one is the name of the array. And then we can just use the pandas data frame to plot this. So we just plot our elements object, and we get a very nice table which shows us all the dates, mean values, maximum values, and minimum values for NDVI. This is then very easy to plot this. Using the matplotlib, we just say that on x-axis we want the date from the table, and on y we want mean, but it is not formatted very nicely. And right here we have added a bit more formatting, and when we also plotted 3 different lines, each one maximum, minimum, and mean. And this is the chart that we have gotten, so that you can compare all the different statistics of the NDVI. And here we also played a little bit and added the plot fill between option to create a very nice looking chart like this. All right, so you can do this for both indices. You can do it for barren soil as well in the same spot like that, or separately, it doesn't matter. It only matters that you append the values to the same arrays. So the final arrays should then look like this. And as you can see, this one that calls for the band name contains both. So that then when we create elements, we can get a table with both of them. Well, alternatively, you could just do this all separately and create 2 separate tables. It doesn't really matter, but then this is how we plotted them both on the same chart. Here I also have an option for you to create a nice looking histograms if you want using Python, but because our request builder is an expert in displaying different histograms, I will not go into detail, but you can check it out yourself later. Let's jump back to our agenda. And the only thing that we have left is a quick mention of Batch Statistical API. So Batch Statistical API is intended for the same operations as Statistical API, but for a lot of polygons. Here we are talking hundreds of thousands, even millions of polygons. You can easily create statistics on a multi-polygon in Request Builder itself, but this is something completely different when you need it, for example, for some machine learning and so forth. So in order to use Batch Statistical API, let's jump to our documentation. Batch Statistical API, here it is. So basically what you would need to do, you would need to create a geopackage file with your polygons and then upload into AWS S3 bucket. You would then create a request to it that would reference the bucket where your geopackage is and also the output bucket. I will not go into detail here because we are planning to make a follow-up webinar or just a video for you to follow. So stay tuned also for that part. And with this, I am returning back to our presentation and I'm saying thank you everyone for joining. And I hope you enjoyed the statistical API and that it will be of great use to you.
Thank you, Munia, for your presentation. As mentioned at the beginning, we will start the questions and answer section now. Let's go first through the questions which were already posted in the group chat. The first question came from Virginia, and she's wondering if there are any Python code for practice the training. So probably you mean how you can go after Munia's instructions. So Munia already mentioned during the webinar that she prepared some Jupyter Notebooks. With the recording, we will share also a link to the Jupyter Notebooks, which they will be on our repository. The second question came from Kremina. Is the statistics calculated over the entire box or over the actual image pixels only? I think my colleague Tomi can answer this one.
Hi, everyone. So in the example that Munia presented, the statistics were calculated only over the actual image pixels because she returned a good dataMask.
What intervals are available? Is there also a weekly interval available?
So 1 day is currently the minimum, and then you can select any number of days. And additional option is to select months, which will select intervals according to month boundaries.
Thank you, Tomi. If there is more than one scene per interval, do we get to choose which one?
You can control which scene you want per interval using Mosaicking order. So you can select if you want the most recent, least recent scene or the scene with the least cloud coverage if the collection has cloud coverage information.
Maybe I think I would like to add here, pretty much here, you can also have multiple scenes in a single interval. So what you can do with a different mosaicing type. So if you select tile or orbit mosaicing type, you can have multiple scenes and, for example, decide that you are going to calculate maximum NDVI for this interval from various amount of scenes and do statistics over that. So that's also an option.
What about dimensions resolution? How this should be set for a polygon?
So that depends on what resolution you want to calculate statistics. If you want to calculate them at the native resolution, you would set the resolution to native resolution, or you could request dimensions that give you a native resolution.
Apart from Landsat, will Sentinel Hub support the use of other non-Copernicus data, for example, from Japan, China, Russia, the Emirates, etc.? If yes, which data and when?
So Sentinel Hub already now supports other options like Maxar and Airbus and Planet. We don't yet have the data coming from the Russian or Chinese or other providers. There are some constraints attached to that. First of all is that they need to make this data available either for commercial or public use. And then they need to provide options to integrate with them. At the moment, we are not discussing yet with any of these so it's not on the short-term period. That being said, we are always looking for additional data sources to connect to the Sentinel Hub. So, I'm confident that in some time, this will all be available.
How to automate the frequency of image collection? For example, accumulate data at each 8 days during 12 years, for example.
One thing to clarify first is that image collection is not under our control, right? So image collection is under control of the data providers. As an example, Sentinel-2 is every 5 days, Landsat is every 8 or 16 days, and so on and so on. And this is, for us, this is given. It is possible for users to order tasking through us, but this comes at a much higher price, and then we would coordinate tasking with, as an example, Airbus or Maxar or Planet, and make this data available. So therefore, if somebody wants to have a collection of data available over specific periods in the future, the tasking is the only option. For the past, there is, the collection, the data are already acquired, and it's not possible, obviously, to fine-tune that. That being said, once the data are available, you obviously can aggregate them. So probably the right term to use here is aggregate rather than collect. So what you do is that you define the aggregation period, aggregation interval, let's say every 8 days, as Monia has shown. And then within these 8 days, you get access to all the data that were collected within these 8 days, which can be either, a few or maybe sometimes even 0. As an example, if you're using Landsat 8, it will not have the data every 8 days at the moment. So anyway, you get the data within that interval, and then you do whatever function you want, aggregation function you want on top of that, and this is then exposed over statistical API.
Thank you, Grega. The next question comes from Matthias, and he's asking, is there a way to get a JSON with values for each pixel of an area of interest with statistical API? And if not, is there another way to get a JSON? I believe Tomi can answer this one.
If you want to get values per pixel, you should instead use Process API or Batch API. Unfortunately, those two APIs do not return values in JSON format, and this is done by design. So because those two APIs return images back, which is more optimal way for transferring and visualizing data.
Can you explain in detail why the statistics are calculated using the pixels of the bounding box of the polygon and not only the pixels that are inside the polygon?
So the area where the pixels that are taken into statistics calculation is defined by the output dataMask of the eval script used in statistics. So if you directly use the provided dataMask, so the input dataMask, that would be your polygon bounding box. So the selection of pixels used to calculate statistics is directly under your control. If you pass through the dataMask, then the result would be precisely what you're asking. So the pixels within the bounding box, if you change that, you can change it any way you want. Those pixels will be used.
Does the statistical API support more complicated calculations? For example, regression, correlation with other data and similar? If not, is such calculation in the pipeline?
No, currently we do not support such calculations directly. You could do something by crafting your intervals in a certain manner and using a very elaborate evil script. But if you do have such an example and if you present the use case to us, we may support it in the future.
Is the statistical API available for bring your own COC collections?
So short answer is yes. Basically, when you bring your own data to the Sentinel Hub, you can do all the services on top of it. Maybe important point is that at the moment, this is supported in the AWS EU Central and US West region, and on CreoDias in a like a beta option, but not yet for the other deployments that we have in place. The CreoDias deployment is still in the experimental phase, so that is something that is coming in production soon. I can answer to the next question on the whether it's possible to do data from several sensors like Landsat and Sentinel in order to basically analyze longer period of time. And the short answer again is yes, it is possible. This can be done by combining two of the approaches. So first one is that you do the data fusion. I would invite everyone interested to check the webinar on the data fusion that was held in February. And that basically what you do is that when you define the data fusion of not just Sentinel-2 and Landsat 8, but you can go back to Landsat 1, 2, 3, 5 if you want, then you can do the aggregation on top of it. One thing to mention here is that at the moment, the statistical API does not yet work cross-deployment. So you need to do the data fusion on the collections that are available on the same deployment and then merge the JSONs on your site. So meaning that you can easily do the statistical aggregation on all the Landsat because they're all in US West region. But if you want to add Sentinel-2 in the loop, this would need to be done separately because, as mentioned, data fusion does not work cross-region.
Then we have another question in the chat right after we finished with presentation. Arki was wondering if you offer accounts for nonprofits that offer more credits than that offered by free accounts.
So we do have a European Space Agency sponsored option, which is called Network of Resources. There is a very simple process to follow, application form where you describe how you'd like to use the data. It shouldn't take more than 10 to 15 minutes. If you go to our website, you will find it very clearly marked. And then you get ESA sponsored account for this kind of use.
Kiria is asking if we need commercial account or is it possible, is it available to all?
So Statistical API is available to all users who have any kind of Sentinel Hub subscription. So you can use it with the trial account, or you can use it with the exploratory, which is non-commercial, or with any of the commercial subscriptions.
Namra asked if also Sentinel-1 option is available for calculations.
Yes.
Is it accessible through a license cost or is open sources? So I believe we already answered this one, right, Grega?
I'm not sure what exactly this refers to, but the Statistical API itself is a proprietary service operated by us, and it's not available as an open source. But you can use this service on both commercial and open data. So hopefully I addressed the question, whichever route it was focused to.
Can we access latitude and longitude information from the JSON data?
No.
No.
Can data from several sources be analyzed, for instance, Landsat 8 and Sentinel-2?
Yeah, I can repeat that. So this specific combination at the moment is not possible because they are hosted on different deployments. But you can, in general, analyze from different sources by using data fusion.
Are we able to do zonal statistics for a given polygon?
By using Sentinel Hub Statistical API, basically, you create a zonal statistics by using the bins option, because then you can say combine pixels to, I don't know, 5 bins. What you don't get out though is that you don't get a, I don't know, shapefile or a geometry of these zones. So that's something that you would need to do as a follow-up process if you would want it to.
Sharan would like to ask something as well.
Yes, thank you. Actually, I wanted to calculate general statistics for certain, like, hundreds of polygons, and can I able to like only like show those forms only in the, like, in some statistical things, graphs, like phenology studies.
So your question is whether you're able to do statistics over hundreds of polygons, or did I get it right?
Yes, right.
Yeah. So again, the short answer is yes. I mean, as long as you have 100 polygons, the easiest way probably is just to run a statistical API for each of them. If you have thousands or tens of thousands or millions of polygons, then the recommended approach would be using the batch statistical API, which Monia mentioned as well, I think.
I would also like to add here that on our GitHub repository, there is a notebook which shows how you can send the several statistical API requests at once for several polygons, so you don't have to manually do them all by hand. And it has a table set up with different land uses, and then it creates visualizations on top of that. So we will also add a link to that to the description.
Yes, and one more thing, I just seen your GitHub repository, but the notebook which you explained, it's not available. Can we able to find that also in the GitHub repository?
Yes, of course it will be added, but the notebooks are quite fresh. So as soon as the recording is on, the notebooks are also going to be on, so, and you will be notified about it, and they will additionally also be linked from the video, so no worries there.
Thank you.
So we have another question. You can unmute yourself to ask.
Thank you very much. Actually, I had a question like let long. Like, say, for example, I have a polygon and I want to also get the let long information, because if I want to visualize in a map or something, yeah. So how I can do this using the process API? Because as you said, we cannot do using the statistics API. So in that case, should we use the process API for this to get also the let long information?
I can maybe try to answer this one. So, I mean, if you have a polygon that I imagine that you already have the coordinates of that polygon, because this is how the polygon is defined. If you want to visualize that polygon in terms of the, I don't know, NDVI image or true color image or whatever, the process API would indeed be the correct API to use. If you want to get for that specific polygon the statistical information, such as the average NDVI over time or at some specific point in time, then you only get JSON value, values in JSON, which are not tied to a specific let long, because they are tied to the whole polygon that you have provided.
Yeah. So in that case, I need to use the process API to get the let long information with the values, band values information, right?
If you want to get the values for each individual pixel, which is tied to each individual let long, then the process API would indeed be correct, yeah.
But there is no way to use the statistical API to get the let long value. We cannot retrieve, right?
No, that, I mean, again, what you need to take into account is that when you have a polygon, this polygon will probably have thousands or tens of thousands of pixels. And it doesn't make sense to do the statistical analysis for each of the 10,000 pixels. Therefore, I mean, for this kind of actions, the raster processing is better, and therefore it's the process API is more suitable. If you want to average the data over some polygon, then the statistical API is the right way. But yeah, there you don't get the data for a specific point, but rather for the whole polygon.
Okay, thank you very much.
In this case, if there are no more questions, we can wrap it up. I would still like to invite you, if you don't have a Sentinel Hub account yet, here are stated a couple of useful links, and among them is also how you can create a free 30 days trial account. If you need more processing units than the trial provides, please do contact us and we will sort it out. And like it was already mentioned previously, if you're conducting research or if you are in a pre-commercial exploitation phase, you can use the opportunity to apply for ESA-sponsored accounts. For more information, you can see other links as well. Thank you for being with us today. Follow us on social media for future webinars. If you have further questions, use our forum. We are happy to help you there as well. Stay tuned, and we hope to see you the next time.